Hello, and thank you for joining this webinar on preparation for the CSWP CAM exam. A little bit about me. My name is Daniel Granillo, and I am a senior application consultant with the SOLIDWORKS certification program. Been with SOLIDWORKS for 3 years now. I am based in Austin, Texas. My background is manufacturing engineering, my degree from Cal Poly Pomona. And with the SOLIDWORKS certification team, I'm kind of the lead support guy for our certification inbox. I support all of our customers worldwide. If you have any questions about our exams or you have a problem with taking one of our exams, most likely you are going to get contacted by me or one of my other two colleagues. But I also help co-author several of our exams, one of them being the CSWP CAM exam that we released this past year. And hobbies, I love to travel. This year I got the opportunity to travel to Alaska. And if you go, I highly recommend taking the helicopter excursion. It was by far the most, the highlight of the whole trip. And we got to go on a little excursion up there. We trekked the glacier for about 2 hours, and it was phenomenal. Take an empty water bottle with you. You can fill up your water bottle with some pure glacier water. It doesn't taste any better than that. And with me today are my colleagues. I'd just like to give a special thanks to Jennifer Tashiro and my technical reviewer, Santiago Laverde. They will be assisting me today, making sure today's webinar goes smoothly. And likewise, if you have any questions, Santiago will be more than happy to assist you filter those questions through me. Likewise, Santiago has a vast experience in the CAM world and supports SOLIDWORKS CAM on the technical support side. So I'm happy to have him with us here today. So in today's presentation, we're going to take you through the exam, the sample exam of the CSWP CAM. There are 6 questions in the sample exam. And we're going to be giving you tips for avoiding the most frequent pitfalls and mistakes when taking the actual exam. Question 4 of 6 there is on finishing. It's very similar to roughing. We're just going to go ahead and skip that question due to time restrictions, but you'll be able to get the gist of the majority of the content from the other 5 questions. And then we'll review the content of the exam at the end and other areas worthwhile for you to study. Now, for the SOLIDWORKS certification for this practice test, where can you go to get it? So for those of you on today's webinar, you can download it. If you're watching this on our YouTube channel, there will be a link down in the description where you can follow it to obtain the link to obtain a zip file for the practice test. Okay, so question 1 of the practice sample exam, I'll just bring it up here. When you download it, you will get a sample exam that will come in come with 2 files. You will get a PDF and 1 SOLIDWORKS part. So opening the PDF document, and we're going to come and scroll down to, I believe it's page 16 of the handout here. And to start off, you must use, says it right here pretty clear, at least SOLIDWORKS 2018 for the sample exam. And the next note, we added, some post-processors selected in the actual exam, they're not suitable for the intended manufacturing process. And of course, they're to be used for testing purposes only. Likewise, during your exam, you don't want to modify any of the default machining parameters unless specified in the actual exam. And all tools have been supplied to you in the Part Models Active Tool Crib. So you don't have to worry about utilizing any other tools other than the tools provided to you in the actual CAD model. Okay. So in this first question of the technology database, the goals is, okay, being able to access your technology database, referred to as TechDB. And like the other one is to link a new file to your technology database. But before you do that, you want to make sure SOLIDWORKS is not running before making this change. And in the handout, we actually spell out the location of where you can find your technology database file. The default file location is under C, Program Data, SOLIDWORKS. SOLIDWORKS CAM followed by the year, so it'll be either 2018 or 2019. And then TechDB. Now, I already have this location navigated to on my end. And when you navigate to this file location, you're going to come across a file called TechDB with the file extension CWDB right here. And so this file, we actually want to create a copy of it and rename it to, so that way we don't write over our production environment database file, and we keep this the original intact. So I'm just going to create a copy and paste it in the same file location, and then rename that file to TechDB, and I'll call it sample exam. Great. Okay, so now that we've copied it over, we want to now link our technology database to this new file. But how do you do that without running SOLIDWORKS? Santiago, do you know?
That you can find the executable for the TechDB, or you can create a shortcut for that if you want to.
Yes, yes.
Yeah, that's probably the best way to do it. I mean, this is something that I normally recommend. If you are going to run your TechDB out of SOLIDWORKS, just create a shortcut for that executable is probably the best way to do it.
So thank you for that. So under C program files, this is the installation of where your SOLIDWORKS is installed. For some of you, if you add a version at the end of SOLIDWORKS Core, it may be, for SOLIDWORKS Core 2019. I know I do that when you have multiple versions installed on the same computer, followed by SOLIDWORKS CAM TechDB app. And when you navigate to that location, you're going to look for an executable file, and it'll look something like this, techdb-app.exe. So go ahead and launch that file. Double click on it, and it will launch the technology database without the need of having to go into SOLIDWORKS. Now, what Santiago was suggesting is you can create a shortcut to this. You can pin it to your taskbar. That way you don't have to navigate to this every time. Thank you, Santiago. Now, under settings, we can browse to our new technology database that we copied over. So that way we're not overwriting the original one. And for the actual exam, it's recommended, actually, to utilize the technology database that comes out of the box, meaning if you've altered your TechDB in any way, you want to make sure you get a clean copy of it by either reinstalling SOLIDWORKS or contacting your SOLIDWORKS reseller and ask them to send you a copy of an original out-of-the-box version. That way there's no complications during the actual exam. So now let me close this and launch SOLIDWORKS. So just take a minute for SOLIDWORKS to pop up. And we can confirm once we have SOLIDWORKS up and running that it's actually, our technology database is actually pointing to this new file that we created. So I'm just going to begin a new part for this, for the sake, and expand my SOLIDWORks. It doesn't look like I have the SOLIDWORKS CAM add-on enabled, so I'm going to go ahead and enable the SOLIDWORKS CAM add-in since it's not coming up on startup. Okay. There we go, SOLIDWORKS CAM. And from here, the technology database, we just click on that, it'll open that up again, and I'll come down to settings, and I see that we are pointing to the technology database. All right, so I'm going to close this and we can proceed to the next step. So question 2, facing. So the goals of question 2 is we're going to look to prepare the part model for changes. We're going to define stock, define the coordinate system, extract machinable features, generate an operation plan. We'll be sorting operations, modifying operation parameters, and generating toolpaths for this next question. And let's dive on into the PDF document. And let me see, question 1 that was completed. Looks good. Question 2. All right. So for question 2, I see open the attached part file containing CAM-01. So the first thing I'm going to do is open up that part file. Go file, open, and open up that part file that's included with your sample exam. And before I even touch anything, I'm going to go ahead and save as. And we're going to save as, what I like to do after each question in the actual exam is just add the question number to it. So Q, we'll call it, this being question 2, we'll call it Q2. This way it doesn't overwrite the original part file should we need to go back and reference it at any time. All right, and then let's see what other details to ask us. Select the appropriate machine post-processor for this question using the details above. Do not use any other tool supplied to you other than the part model's active tool crib. I don't know if you guys can see this, but this line item right here, do not use any other tools other than the tool supplied to you. So that's very important. We do not want to add any other tools. And as a tip, in SOLIDWORKS CAM, we're going to first select the appropriate machine and the post-processor. It's found in the details above. So I see we have a unit system is millimeters grams per second, and this part file is in millimeters grams per second. Let's see, document units, we got 2, looks great, just confirming. And then the machine name is millimetric, post-processor, achromatic 2100. So I'll just, it's kind of, so another tip is to utilize dual monitors when taking this actual exam. That way you can have the exam question on one screen and your SOLIDWORKS running on the other. All right, so under your SOLIDWORKS CAM feature tree, we will go ahead and let's go ahead and edit the machine details and confirm the machine as well as the post-processor. So for the machine name, I see, okay, we are using millimetric, so that's good. The post-processor, I come over to the post-processor tab, and Achromatic 2100 is selected, so that's good. And the last thing it mentions, do not use any other tools other than the tools supplied to you in the Part Models Active Tool Crib. So if we come over here to the Tool Crib tab, you'll notice that this part file has, it has some tools already in the Tool Crib. So there's a nice little checkbox right here that says use Tool Crib tools only. So I want to go ahead and check that checkbox just so that way SOLIDWORKS doesn't add any other tools from our technology database. All right, step 3, now we're going to go into and define the stock of our material. And see, we got 6061 T6 aluminum. So I'm going to come into the stock manager, right click and edit that definition. All right, material 6061 T6 looks good. Stock type extruded sketch. So under our stock type here, currently selected is the bounding box. What we want is extruded sketch. So I select extruded sketch, and it says use the sketch name stock from the feature manager design tree. So if we expand our feature manager design tree, we'll see that, okay, there is a sketch at the bottom labeled stock. So I'll go ahead and select that. It gives us a nice little preview. Depth is 60 millimeters, so set that to 60. All right, and we're going to go ahead and reverse that direction. So that way our stock encompasses our part model. And so now our stock size should be 350 millimeters, Y direction 250, and Z is 60. So I see, okay, I confirm that right here under the stock size, and that matches with our document. Okay, moving on, step 4. So we can go ahead and accept this at the top, say okay, that looks good, we got our stock. Step 4 now is defining the coordinate system. So to use the upper left stock position as shown in image 2, make sure the Z direction is correct. So I'm right here at step 4. Image 2, let's take a look at that. Image 2, okay, so I see image 2 here, and the Z direction is in the top left corner, pointing up. So that's what we want. So let's go ahead and define our coordinate system. We're going to right click on our coordinate system and select edit definition. And for the origin, we're going to select the stock bounding vertices. And here we'll be able to select, okay, which corner do we want our coordinate system to be on. So we're going to select the top left corner, and I see, okay, we have the Z direction is pointing up in the correct location, as well as our X-axis and our Y-axis as well. So this area for defining a coordinate system. You want to be very familiarize yourself with it. Likewise, part bounding box, that's utilizing just the part, for the vertices. But in this case, we're utilizing our stock as our vertex, the top left corner. So I'm going to select OK to that. Okay, now coming to step 5, let's see, extract machinable features. So we're going to extract the following machinable features and strategies. We have a face, perimeter open pocket, rectangular pocket group, and a counter bore hole group. Note, you will make a custom machining strategy for the counter bore hole group in one of the next several questions. Okay, so for this operation, we're going to let's see, make sure that we can perform these operations from the, see, let me expand this. There we go. So we want, what we're looking for is our SOLIDWORKS CAM options. So I'll open up our SOLIDWORKS CAM options dialog box. And so the intent of this question is we're going to use AFR, automatic feature recognition, to extract these machinable features. So first step would be click on extract machinable features, and I see, okay, that SOLIDWORKS extracted a face feature. We have a part perimeter open pocket. We have a rectangular pocket, and we have a counterbore hole group. Let's review the PDF document. All right, so we have our face feature, we have our perimeter open pocket, we have our rectangular pocket group, and we have our counterbore. Looks good. Now, if you're not getting any of these features, go into your SOLIDWORKS CAM options, and under, I believe it's features, you want to make sure that it can extract these specific features. You just have to turn them on by check mark. Step 6. All right, now we're going to go ahead and generate an operation plan for all the features except the counterbore hole group. So do not create an operation plan for the counterbore holes at this time. So how do we do that? So you can pre-select, the face feature, you can select the perimeter and the rectangular pocket group, and then generate operation plan. And so now we're on our CAM operation tree, and I see that there's an operation for the roughing. I see that there's some contour mills, everything except that face feature. It looks like an operation didn't get created for that face feature. So what we'll have to do is create an operation for that manually. And I can tell because it's in blue under our CAM feature tree. All right, no biggie. So if we right click on that face feature and select create operation plan, let's see, do we get it? No. We may have to manually create that operation plan from the operation tree. To do that, right click on mill part setup, 2.5 axis, and this was going to be a face mill. And these are all the kind of complications that you may get, during the actual exam or even in real life. So it's good to be able to troubleshoot these issues and know how to create these operations on the fly if needed. So I'm going to select face mill. And for the tool, let me just confirm with the PDF document. For the tool, it says, let's see, modify the facing operation parameters. Okay, now I'm just skipping step 7 for right now. So step 7 says sort operations right here. We're going to go ahead and skip that and move on to step 8, where we're going to actually create an operation plan for the face mill and then come back to sorting these operations. So I see that the face mill, the facing operation is utilizing the 100 millimeter 9 flute face mill. So we have that selected. Great. Now under features, we're going to go ahead and select the face feature. That looks great. Okay. And under operation, what do we have selected? We have edit operation on creation and name operation on creation. I'm going to unselect the name operation. We don't really need to rename that, but we do want to, do we want to edit it at this time? No, I don't want to edit it at this time. I just want to create it. Okay, great. So now we have the face mill in our operation tree. I see that here. And so now we're going to go through and sort these operations as read from step 7. So how are we going to sort it by? We're going to sort it by facing first, then rough, and lastly finish, contour mill. And so under the operation tree, we have an option, to sort operations. So selecting sort operations on the sort tab, we can select, okay, I want to first sort by face mill. Okay, that's good. Then we want to sort by rough and then finish. So there's my rough. I'm just going to drag that right underneath face mill. And finish, otherwise known as contour mill, we're going to drag that up right underneath rough mill and say apply. And okay, so you can see now our operations have resorted accordingly. So we have our face mill followed by all of our roughing operations and our finishing operations. And then lastly, we have a drill. So now let's refer back to the PDF document. Now we're going to go through and modify the facing operation parameters. So this is where the two monitors comes in handy. I'm going to just collapse our SOLIDWORKS real estate area accordingly, and we're going to go and modify this face mill operation. So I'm going to right click edit definition on our face mill, and I see that, okay, the face mill tool 100 millimeters, 9 flute face mill, okay, check. I see that here. For the feeds and speeds, we're going to move over to the next tab and make sure that it's defined by library. Okay, I see that's good. The Z feed rate. So down below under feed rates, I see that we can modify the feed rates accordingly. So we're going to actually adjust this to a percentage as indicated on the exam. So the percent, we're going to set that to 25%. And the lead-in feed rate is 75%, so that looks good. Next is, I see max step over is 70% and minimum side offset 20%. So for that, we're going to move on over to the next tab in our operation parameters. So under facing, I see, okay, here now I can set the max step over amount. So that looks good, 70% right there. Max side offset is 30%. So let's change this value to 30. And you don't want to modify any other, so in the actual exam, you don't want to modify any of the other values unless specified. Okay, so minimum side offset is 20%. So let's change that, bump that up to 20. The first cut amount I see is 3 millimeters. So right here under depth parameters, first cut amount is 1 millimeter. So we'll set that to 3 millimeters. And the max cut amount is 3 millimeters. So change that to 3 millimeters. And you just want to keep in mind that, make sure that these values here, just as a tip, it says millimeters, because there's a little icon here that you can change it to percent, And very often I see sometimes test takers, they'll actually enter, the percent, icon will be selected, and it'll just say 3 without the millimeters, and they think, oh, it's 3 millimeters, but that's actually 3%. So make sure that, you're entering numerical values and not percentages. Right, Santiago?
Yes, Daniel, that's what you have to pay attention. Whenever you click on the button, make sure your percentage is off or on, depending on your needs.
Yeah.
So make sure you see the units. I mean, if you don't see units, you're in percentage.
Mm-hmm. Thank you. And so for the cut method, we have here is climb. So, all right, that looks good. Cut method is climb. The clearance plane, all right, so it says top of feature, distance 3 millimeters. To set this value, we're going to move on over to our next operation parameter tab under numerical control NC. And here I see that the clearance plane is set to top of feature and the distance is already set to 3 millimeters. So this is another area where test takers overlook, is not setting the clearance plane and see top of feature. So yeah, you want to make sure, because you don't have any other clearance plane selected unless otherwise specified. So in the actual exam, it could be top of stock. But in this example, we're using top of feature. All right, that looks about it. So I'm going to go ahead and select OK to save these before I lose them. And save often, right? So that way you don't lose anything. So I'm going to go ahead and click the Save button now before we get too far ahead. All right, so now the next step is to now generate toolpaths for the facing operation. So we're just going to generate the toolpaths for this one operation. So I'm going to select Generate Toolpath, and we have our toolpath. So in this question, it's asking, what is the estimated machining time in minutes for the facing operation? Where do we go to find that information? Well, we can double click on the operation itself, edit definition, and that will open the parameters dialog box. And at the very end is this optimize tab. And under optimize, here we can see, okay, we have the estimated machining time specified for, we have time in minutes, and we have the toolpath length. So in this question, we are asking for what is the estimated machining time in minutes for the operation. So for this operation, the total machining time is 8 minutes, 1 second. So the answer would be B. There we go. And we'll say OK to that. And save this now. All right, question 2, done. All right, next, moving on. Let's get back to our PowerPoint very quick. So, question 3, roughing. The goals of this question is we want to modify the roughing operations and then utilize the combine operations command just to help us save time, because you notice that we had several different roughing operations. We can actually combine them to save a bit of time. And in the actual exam, if you can save some time, that's going to really help benefit you. And then generate the toolpaths. So going back to our part model, I see, okay, we have 1, 2, 3 roughing operations. And going back, referring to the PDF document, it says use the part from the previous question and now modify the roughing operations for mill part setup 1. It says all roughing operations parameters for mill part setup 1 use the following information. Tip, here we go, combine roughing operations to save time. Okay, so what I'm going to do before editing any of the operations is combine them. How do we do that? So I'm going to select all 3 roughing operations and right click, and you'll see here that we have an option to combine operations here. So selecting combine operations. Yeah. All right. And so we're going to combine all 3 of these rough mill operations into one. And so we're going to select OK to this action. And I see now in our feature operations tree that all 3, if I expand rough mill 1, there's the perimeter open pocket and we have the rectangular pocket group, both under the rough mill 1 operation. Okay, so now we can proceed with modifying this one roughing operation parameters, and it will trickle or default all the roughing operations to this one, so to save time. So the roughing tool, we have a 20 millimeter carbide 2-flute end mill. Let's see, and we can confirm that on the tool tab. So I see here, this is the 20 millimeter 2-flute. All right, feeds and speeds, we have selected, okay, it's defined by library. Z feed rate is 25%. Leading feed rate is 75%. So I'm looking right here, and right now we have 50%. So we're just going to go and bump this up to 75. Okay. Now the roughing pattern is says pocket out. So moving on to the next tab under roughing, our pattern is pocket out. That looks good. We have several different options for patterning, and you want to familiarize yourselves with all of these different pocketing patterns. And for this selection, we're going to keep pocket out. The side parameter, I see step over is 60%. So under side parameters, our step over is 40%, so we're going to bump that up to 60. And make sure that, this is percentage and not, when we convert that to millimeters, look, it's actually 12 millimeters. So make sure that we're, if it says percent in the exam, that you enter a percent value. And you can tell because it doesn't have the units assigned to it. Okay, that tells us that, okay, this is actually a percentage. The cut method I see is conventional. So cut method is set to climb right here. We're going to go ahead and change that to conventional. Max cut amount, first cut amount. So first cut amount is 70%. And we're going to bump this up from 50 to 70. The max cut amount, we're going to bump that up to 100. And final cut amount, we're going to set that to 0.2 millimeters. Okay, now for the clearance plane, we're going to move on over to, once we're done with the roughing, move on over to the NC tab. And this is where we can set our clearance plane. So the clearance plane is set to top of feature with a distance of 5 millimeters. So currently it's set to top of feature at a distance of 2.5. So we're going to just bump that up to 5 millimeters. and I can type MM just to make sure that it takes it. Entry method, we have it set up for ramp at an angle of 5 degrees. So for the entry method, we're going to actually move on to the next tab under feature options. And here you'll notice we have the entry method. It's currently set to plunge, and we're going to change that to entry to a ramp entry, and with the angle of 5 degrees. So currently the ramp angle is 3. We're going to set that to 5. Okay, and here's another tip. How often do you see this, Santiago, where the user, he sets the entry for this value, but he doesn't set it for all? So, you know, we did have 3 roughing operations originally, and we combined them into one. Now, this doesn't affect all 3 operations unless there's this little icon here, and I'll zoom in on it. It says apply to all. So you want to make sure
it'll apply to the perimeter open pocket 1. If you see on the features on the top of the box, the same tab, it'll apply to that only operation if you don't hit that button.
Yeah, so you want to make sure you select that icon to apply this entry to all. So we get this little dialog box that says change entry type parameters for all features. Select yes, I want to apply it to all of the features. And we're good there. Now we can move on. And oh, it's even indicated right here in the exam, apply ramp entry method to all. So it doesn't spell it out. That's why we're describing it in this video. Now, all right, moving on. It looks good. So I'm going to say OK to this step 1. Moving on, in the PDF, we have generate toolpaths for the roughing operations, and then it's asking, what is the estimated machining time in minutes for the roughing operation? All right, so we're going to right-click on our rough mill 1 now, and generate toolpaths. Okay, that looks good. And in the actual exam, you know, there'll be images, so you can, you know, refer to the images to see, okay, how closely related are your toolpaths to the image in the actual exam. So I see there's 1, 2, 3, there's 4 levels in the Z direction, and our toolpath has 1, 2, 3, 4. That's a good indicator that shows we're on the right track. So what is the estimated total machining time now? To find that, we're just going to right-click on our rough mill 1, edit that definition, and on the last tab, we have the optimize to where we can actually see the estimated machining time for the roughing operation. And so the estimated machining time with rapid, feed, and non-cutting, I see is 67 minutes, rounded off 67.01, and that's going to give us our answer be A, 67.01. All right, great. Say okay to that. So what am I going to do now? Save. Yeah, but this time we're going to save as. And in the actual exam, do the same thing. Save as after every question. I'm going to label this question 3 and save that over. So that way we don't overwrite question 2 in case we ever need to go back to it. So moving on. So question 4, we're actually going to skip this question in this video, but it's very similar to question 3, where we're going to combine all the finishing operations to save time, and then you know, specify all the parameters for the finishing operation, and then generate toolpaths and find out what's the estimated machining time in minutes for the finishing operation. So by selecting your 3 contours. You can right-click, combine operations into one, and then now we have just one to modify instead of 3 different operation parameters. And then you can come in here and start modifying the values accordingly. I will say the lead-in and lead types, so if we were to modify this, is found under lead-in. So here, this is where you'll specify, things like the lead-in type, so perpendicular, the lead-in overlap, and as well as the lead-out. And so in our operation parameter, you'll see the lead-in type is set to arc, so you just change that to perpendicular. And then the lead-in overlap is 1 millimeter. So here I see, okay, it's utilizing percentage, so we're going to change that to a numerical value. And I see, okay, that's 1 millimeter, that's great. Lead out type is same as lead in. So that's specified there, that looks good. And then apply lead in, lead out to all. So likewise, how we saw with the roughing operation, with the ramping, there was that special icon there to apply it to all. Well, for, the lead-ins, for, the finishing, there's a checkbox here to apply the lead-in, lead-out to all here. So I'm just going to say okay to that. I'm not going to modify any of the other values because it's so similar to the roughing. So moving on is chamfers. And I love chamfers. And by just, coming back to our presentation, with chamfers, you actually have to utilize IFR, interactive feature recognition, and then specify, know ahead of time what kind of feature edges you're going to be working with. If it's going to be apex or outer edge. Santiago, do you happen to know, like, is apex or outer edge, like, where would we use apex? Where would we use outer edge?
If you have the physical chamfer, you can use the outer edge, or if you don't have it, you can use the apex. That's pretty much what we normally do if you don't have the feature by itself.
Yeah. So what Santiago is saying, for outer edge, if the chamfers are modeled in your actual model, if they're designed in, then utilize the outer edge. Otherwise, if we look at the inside pockets, there's no chamfers modeled in. But on the blueprint, it's very common. You'll see, okay, break all edges, 20 thou. So in this scenario, you would utilize, in that scenario, you'll utilize the apex method for machining those chamfers. Great, thank you, Santiago.
No problem.
So yeah, so I mean, most likely, the chamfers are not going to be modeled in a typical design, but for the actual exam, you want to familiarize yourself with both apex and outer edge. So let's demonstrate that utilizing the sample exam. So in the sample exam, I see we want to create the feature, operation, and toolpath required to machine the chamfers using the following information. Finish strategy is set to finish, and the tool, we're going to use the 20 millimeter diameter 90-degree countersink tool. We have some parameters here that we're going to set by, and we're utilizing the outer edge method. Likewise, under machining parameters, this is something to pay attention to, is the clearance. The length of our chamfer is going to be 4 millimeters versus the clearance is set to 2 millimeters. So you want to make sure you give yourself enough machining depth to compensate for that clearance. What do I mean? So in this top image here, you'll see, okay, this is the clearance, 2 millimeters, where the tool tip actually protrudes surpassing the actual chamfer edge of 4 millimeters. So let's do this. Let's perform this in our. Let's create this feature in these operations. So I notice, we don't have an operation for these, so we have to actually create a feature for this. To do that, right-click, make sure you're under your CAM feature tree, and right-click on Mill Part Setup 1, and we're going to actually create a 2.5 axis feature. Okay. For the type, this is, so in the actual exam with 2.5 axis features, you want to familiarize yourselves with all of these, with pocket slots, corner slots. In this instance, the chamfers are on the outer edge. And so we're going to actually create a boss feature. Selection filters, we're going to, just select the outer loop. So here I'm going to select the outer edge of our chamfer. Okay, and then that's pretty much it. Now in the next step, we're going to set the end condition or the machining depth. So I'm going to select the end condition tab and move over. And this is very important when utilizing the clearance for chamfers. So here we have our clearance set to 2 millimeters. So we want to make sure our depth is at least 4 millimeters deep plus 2 millimeters. So that equates to, what, 6 millimeters? There we go. Now, and I'll share why once we do this, because with the chamfers, when creating a chamfer operation, you want to make sure that you have enough machining depth to compensate for it. And we'll select OK to accept that. And I see, okay, we got the regular boss here. Beautiful. All right, so now let's create an operation for our chamfer. So I'm going to move on over to the operation tree. Right-click on, so I am on the operation tree. I want to right-click on Mill Part Setup 1, and now create a 2.5 axis mill operation, and this is going to be a contour mill or a finish. For our tool, we're going to select the 20 millimeter by 90 degree countersink tool. And for the feature is we're going to select the boss feature that we just created. And I'm going to go ahead and for the operation, turn on the edit operation parameter as well as name operation parameter. And so when I say OK, it's going to ask me, okay, what do I want to name it? I'm going to go ahead and call it chamfer. And I'll put in parentheses outer edge and say OK to that. So it renames it in the tree, and it dives into the parameters for this tool. So I see, okay, we got the 20 millimeter countersink tool, we got feeds and speeds, and in the exam, I see that the feeds and speeds is set to library. So library, we're good here. The Z feed rate is 25%. That's good. Lead-in feed rate is 75%. That's also good. So moving on to the chamfer machining parameters. So you won't see chamfer up here, but you will see contour, or AKA finishing. And under the contour tab, here we have this checkbox for chamfer machining. And so when we utilize that checkbox, all the other options for cut method or for the depth parameters grays out. So now we're, okay, we can specify the feature edge. Do we want this to be apex? Do we want this to be outer edge? For this problem, we're going to select outer edge. For the length, we're going to set that to 4 millimeters. And for the clearance, we're going to set that to 2 millimeters. Okay, so that looks good. I can actually preview that, and I see that it gives us a little preview of the toolpath for that chamfer. Now, what if the clearance was, say, I don't know, 3 millimeters? Would I be able to set that to 3 millimeters? Let's find out. No, we're not. We actually get this little pop-up message that says the chamfer length and or clearance exceeds the machining depth of 6 millimeters because we actually set that machining depth ahead of time to 6 millimeters. Either define the feature as a through feature or override the machining depth on the features option tab. So basically what this is telling us, and it'll set it back to 2 millimeters, is if we wanted to have a clearance plane that goes deeper, we have to actually modify that feature under the feature tree for the rectangular boss. And to do so, we can come back into it, modify it, go to the end condition, and here either increase this to, say, 7 millimeters, or there's actually a checkbox right here that says through. And by selecting the checkbox through, we'll be able to overwrite that value by saying OK. So when we come back to our feature operation tree and under the chamfer outer edge, now since it's a through machining depth, we can modify the chamfer to be, I don't know, we can say we want a clearance of, say, 6 millimeters if we wanted to. And it'll give us a nice little preview of that, and it'll take that very nicely. So, but for this, we're going to go ahead and set that to 2 millimeters as specified in the sample exam. So oftentimes I see many test takers get hung up on here when they find out that they actually set their machining depth to the length of the chamfer and they weren't able to compensate for the clearance. So just a tip. And then moving on, the clearance plane, it says top of feature, distance of 3 millimeters. All right, moving on. So on our NC tab, I see that our clearance plane is set to top of feature, a distance of 3 millimeters. So we're good there. Now simulate the tool path to ensure the tool is not cutting into the part. So often do customers do, I will get models in and say, hey, review our part. And I ask, well, did you simulate, the part file? Did you simulate your tool paths? And oftentimes they say, nope. So I would suggest, go through and you can simulate tool paths. Make sure that your tool is not running into your part. So if we just right-click on this chamfer, we can step through the tool path. And would you agree, Santiago? With anything, you want to make sure you simulate, your tool paths. Make sure
that's what we have simulations for, so you don't crash your machine.
Yeah, the whole point of the program. Yeah. So we can right-click on it, simulate the tool path, and we can, show the difference, in the actual stock to make sure that, okay, we're not cutting away any unwanted material. So make sure you simulate. Now, what is the total, or what is the toolpath length for feed in millimeters for the chamfer? So this is somewhat of a different question. Now we're looking for feed in millimeters for the chamfers. Do not include rapid. So what are we looking for? We come back to this operation, right-click on that chamfer and say edit that definition, and we can find that under the Optimize tab. Now under estimated machining time, you'll see that there's a toolpath length, and so this is the value that we're looking for. And so for the feed, we are getting a value of 860.94 millimeters. So In the sample exam, I believe that's option C, and say yes, okay, that looks good, and accept that, and now we're moving on. And you can even double check your answers. In the sample exam near the end, there's an answer key where you'll have all the answers that double check for yourself. Now the final question here, we have drilling operations. And with drilling operations, we're going to utilize interactive 2.5 mil operations. The goal is also to create a custom machining strategy. Many companies, they have their own custom machining strategy for doing reaming, for threading, for tapping, in this case, counterbores. So then go through and create a custom machining strategy and utilize the save operation plan to save out this custom machining strategy we create for future use. So let's dive on in. This is our last question. Let's go refer back to the PDF document, see what is it asking us. So in this PDF document, it says, okay, use the part from the previous question. Great. Oh, I almost forgot, save. So let's go ahead and save this off now. File, save as, and we're going to save this off as question 4. Save as, okay. Well, actually, it's question 5, not question 4. We skipped question 4, remember, Santiago? That was question 4 was
we're not going to finish. Yep.
Yep. Okay, so question 6. So use interactive mill operations to generate an operation plan for the counterbore hole features using the following operation sequences and associated parameters. So under our feature operation tree, we have counterbore hole group. So that's counterbore hole group number 2. And what we want is to create several different operations for this counterbore hole group using this distinct sequence of operations. So I see operation 1, we have a center drill. Operation 2, we have our drilling 13.5 millimeter drill, and then scrolling down, just getting a highlight. Operation 3, we're doing a hole contour mill, so that would be the actual counterbore, and I believe that's it. So total of 3 operations. All right, so we'll use interactive mill operations to generate an operation plan for this counterbore hole group. In SOLIDWORKS, since we already have the feature created under our operation tree, right-click on mill part setup 1, we will create a hole machining operation, and this operation will be center drill. So we're going to go ahead and select center drill, and there's other drilling operations this exam covers, such as drill, countersink, bore, ream, tap. Familiarize yourselves with all of these, most definitely, because you don't know what type of question you're going to receive in the actual exam. So for this operation 1, we're going to create a center drill, and it says the 6 millimeter by 60 here. So make sure we have that center drill selected. Okay. Under the features, since nothing's selected, this is going to be for the counterbore hole group. So select counterbore hole group, and under operations, do we want to name it on creation? No, I'll leave that unchecked, but I do want to edit the operation. So I'm going to accept that by choosing OK. And see for the tool, that's great. We have our center drill, 6 millimeters, our 6 millimeter center drill. Shank diameter, 6 millimeters, that looks good. Feeds and speeds, is defined by library, and I'm just moving down now for the operation parameters for operation 1. So the type is spot drilling. So under the center drill tab, we'll find the different types associated with this drill. So spot drilling is the type that's being asked for. Dwell is set to 1. Clearance plane, I see is top of feature with a distance of 3 millimeters. So moving on to the NC tab, top of feature. Okay, that's pre-selected. 3 millimeters, looks good. And then lastly, machining depth of 5 millimeters. So we'll find that under the feature options. And the machining depth I see here, it's preset at 50 millimeters. So that's not what we want. We actually want to go down. It's specified at 5 millimeters. So what can you do? You have two options. One, you can overwrite the machining depth here, but the preferred method is to go into the parameters and set that value. So we're going to go from the top of cylinder 1. So cylinder 1, it even gives you a little preview. So and then we're going to go to the bottom of cylinder. Oh, Santiago's got to go. Of cylinder 1. So that depth is 12 millimeters. So since we only want 5 millimeters, we're going to change this to, let's see, cylinder 1. Here we go. To the top of cylinder 1 and specify an offset. So we can go to the bottom and specify the offset here. So just calculate the difference between 7 and 5. So depth, nope, wrong way. So let's see, to the top of cylinder 1, and we want to go 5 millimeters. There, now our depth is set to 5 millimeters, and I see it gives us a nice little preview here. And accept it, say OK, and we are almost done. So operation 2, we're going to say OK to this, and so we have our center drill. Now operation 2 is we're going to perform a drill and then finally a contour mill for the hole. So we'll come in here in SOLIDWORKS under the operation tree and do the same thing. Specify a hole machining operation for a drill. Here we're going to set that to be a 13.5 millimeters. And for the feature, select your counterbore hole group and accept that. So going through, feeds and speeds is defined by library. That looks good here. Drill hole parameters is set to pecking. That looks good. I'm looking here at our parameters. The sub peck amount is 10 millimeters, so we're just going to set that value to 10 millimeters. Dwell is set to 0. Clearance plane, top of feature, the distance of 3 millimeters. So top of feature, distance 3 millimeters. And lastly, the machining depth is 55 millimeters. So from the top. So if we click on the parameters, I might have gone too fast. Let me cancel that. So select parameters. And we're going to go from the top of cylinder 1 to the machine depth is 55 millimeters. So that's actually going to the bottom of cylinder 2. So that right there, the total depth is 50. So by offsetting an additional 5 millimeters, we'll achieve a value of 55 millimeters here. And accept that, say OK. So it's actually going, we're actually drilling past, through the hole. Say OK. Machining depth I see here is now set to 55 millimeters. That looks good. And accept that value. Say OK. And then lastly, the whole contour mill, operation 3. Now this is going to be for, we're now machining the actual counter bore. We're going to right click on mill part setup 1, add a whole machining operation, and select contour mill. For the tool, we're going to use, it says the 10 millimeter diameter flat end. So we're going to select the 10 millimeter flat end. Looks like it's tool 02. Features, we're going to select the counter bore hole group and accept that. Say OK. And then lastly is defining the operation parameters. So for the feeds and speeds, it's going to be defined by library. And I'm looking here. Z feed rate set 25%. That looks good. For the lead-in feed rate, 75%. That looks good. Side parameters. So now we're getting into the contour itself. Side parameters, it says we're going to rough pass the previous allowance of 0 millimeters. So side parameters here, I see it's set to 0, so that's good. The cut method, we have set to climb. That's good. First cut, 6 millimeters. So here, notice there's no numerical value. So it's utilizing percentages. In this case, we want millimeters. So I'm just going to select, click on these little icons here to convert to numerical values. So for the first cut amount, I set that to 6 millimeters. And for the max cut amount, I set that to 6 millimeters. And final cut amount set to 0. Clearance plane, you want to make sure you know where to go for these, so you're not looking around. So we know that to set the clearance plane, it's found on the NC tab. That's top of feature, distance of 3 millimeters. That looks good. And then lastly, what do we want to cut? We want to cut out the cylinder hole diameter of 25 millimeters. So if we go under the parameters value, cylinder 1, I see that cylinder 1 here is has a diameter of 25 millimeters. That's the whole diameter that we want to cut. We don't want cylinder 2. And it even gives you a little preview of what cylinder 2 is. That's the minor hole diameter. We want cylinder 1, which is the counter bore cylinder. Okay, and the machine depth is set to 12 millimeters. So that looks good. We're going from the top of cylinder 1 to the bottom of cylinder 1, and our depth here is 12 millimeters. So that all looks good. I'm going to say OK to this. And lastly, we have some additional parameters. For the entry method, we're going to set that to none. So here, that's already pre-selected. Entry method set to none. For lead in, lead out, we're going to move on to the next tab to specify that. Lead in, lead out is we're going to select gouge check. So make sure your gouge check is selected. Oh, disable gouge check, it says. So we're actually going to disable that. Disable gouge check. For the lead in type, we're going to set that to perpendicular. So lead in type here, it's currently set to arc. So I'm going to change that to perpendicular. Lead in, lead out type is same as lead in. So that looks good. And then apply lead in, lead out to all. So the last one here, we're going to make sure that this option here under the lead in for applying it to all is selected. And then say OK. Wonderful. Now the last thing, step 2, It says generate toolpaths for the counterbore hole operations and then simulate. So I'm going to come here and select all 3 of these operations and now generate our toolpaths. We get a nice preview, and like I said, we can simulate them. So we can pre-select them, right-click, and now simulate. Let's see, simulate toolpath. So we can move step by step, or we can play it all the way through and show, show the difference. And I see that our counterbores are being machined beautifully. So that's exactly what we want. Now, we don't have any finishing on the sides because we didn't specify that for the outside. We skipped that question, number 4. But lastly, what is the estimated total machining time in minutes? Oh, I'm sorry, step 3, save operation plan. So this is probably like the most important part, is the save operation plan. Once we have our strategy defined, the next final step is to create a save operation plan for this new strategy. How do we do this? So under our feature cam tree, we're actually going to right-click on the counterbore hole group, save operation plan. Here we go. So we want to right-click on that and simply save the operation plan. And do we want to overwrite the existing feature? No, we want to create a new feature condition. And for the strategy, this is going to be for a new strategy. And we're just going to call this counterbore dash sample exam and say OK to that and accept the feature conditions. So what that'll set us up for, if there's any additional parts that has these same counterbore holes, we can utilize that save operation plan, so that way we don't have to go through and redefine the center drill, the contour mill to machine these counterbores. So lastly, what is the estimated total machining time? Now, since we skipped step 4, our answer is not going to be the same, but I can share with you to get the machining time for all the operations. You would right-click on mill part setup 1, edit definition, and under statistics, this is where you would go to find the total machining time for mill part setup 1. So right now, our total machining time is 77 minutes, but since we skipped the finishing operation, that actual answer is 86 in the exam. So I want to make sure you arrive at that final value. All right, so that concludes this sample exam. Let's dive back into our PowerPoint here. So just to recap, what we touched on today, we looked at the technology database in question 1. You want to make sure you utilize the database that comes out of the box and make a copy of it, and then link that copy to your technology database when taking the actual exam and the sample exam. In question 2, we did the whole facing operation, and we utilized AFR. You want to familiarize yourselves with defining the machine, the stock, coordinate system. We sorted the operations distinctively, starting with first facing, then roughing, and then finishing contouring. Extract machinable features, generate operation plan, toolpaths, modifying the operations. In question 3, we did rough milling, and we saw how similar that was to finish milling or contouring. And question 5, we utilized the IFR interactive feature recognition and for the chamfers. And I can't reiterate this enough, but simulate your tool pass. Make sure that you're not cutting into the part. And then in question 6, we created a save operation plan for our counterbores. We did center drilling, we did drilling, and we did the contour milling for that counterbore. Now, this is just what we touched on today. There's still other areas for you to study, and that would be countersink, multi-step hole, tapping, reaming, as well as engraving. You'll see questions on the exam for you might, instead of chamfering, you might receive a question for corner round machining or fillets. You want to make sure you are very well versed in the technology database where you can go in there and you have no problem creating a new tool, as well as modifying any of the existing tools in there. If there's a design change in the actual 3D model itself, how does SOLIDWORKS CAM update those operations and creating a void and contain areas, as well as you will have, I can tell you, a problem with regards to a water jet, plasma, or laser. So make sure you're familiar with those machining operations as well. With that, in summary, take the sample exam. It covers about 60% of the requirement needed to pass the CSWP CAM exam. You can download a copy of the sample exam here. This link will be displayed in the description. Likewise, if you have access to this recording, you can download the zip file. And for additional training, please visit mysolidworks.com or contact your local SOLIDWORKS reseller.